all these forces, are they due to a bending moment? Are they inducing an axial loading? Are they inducing shearing stress? Or are they inducing a torque? Okay, how to do this? Okay, so again, I've developed very unique analysis protocol because of the amount of experience I have and also the amount of problem I've solved. Okay, so you don't get this from the textbook. I'm going to make this easy for you. Okay, so the first thing we have to do is we are going to identify. Okay, we're going to identify the moments right, the axial force, shear force, and torque. Okay, on acting on elements H or K. Okay, why we need to find the what are the stresses and torque acting on the elements is because we have to put them into element form. Then we can construct our what? Then we can construct our mole circle. Okay, so the first thing we have to do is we have to locate. Okay, so first thing we have to do, number one, is we are going to locate. Oh, number one, come on. We are going to locate the orientation of the transformation. Okay, of the transformation and position of the elements. Okay, that's the first thing. Then after that, the second thing is to identify the neutral axis relative to elements H and K. Okay, and then the third rule or the third thing that you have to remember: do not analyze the forces that are dots and crosses. I will elaborate on that. Okay, don't worry. You say, oh, what is this? Or but what is this? Don't worry. I'll elaborate. Okay. So the first thing is to locate the transformation. Okay. So transformation. So we're going to follow. What do I mean by transformation? So you have your x. Okay. This is your y, and this is your z-axis. So if you were to draw this, this is our transformation relative to the elements that we will not change at all. Okay, if you change this, it gets really confusing. So this is your x, this is your y, and that is your z. Okay, then we're going to identify the neutral axis of h again. Now we have a 3D problem, and we are solving it on a 2D world. What do I mean by 2D world is the piece of paper is in 2D. Okay, so how do we go about solving a problem like this? Okay, so we're going to solve the problem in 2D. Okay, and then we're going to you understand what I mean when you look at the process. Okay, so now let's solve the problem in 2D first. Okay, so I'm going to copy and paste. When I say 2D, what do I mean? Okay, so now, okay, watch my orientation now. Now the first thing we're going to do, we're going to we're going to view the structure in this view. Okay, so this is my X and this is our Y. Okay, you guys can see that now. Okay, right? Then we are going to draw the view now. Okay, we're going to draw the view now. So the view, so our pipe look like this. So you have oh sorry, you have 4, 4, 6. So you have okay, so you have 4. Okay, if it's not to scale, it's fine. Okay, 4 and 6, 2, 4, 6. Okay, so this is then you have a vertical section of 10. Okay, so this is just a sketch. So you have 2, 2, 4, 6, 8. Okay, this is just a sketch, as I said. Okay, right. So from here, right, we are going to identify the neutral axis relative to the element H and K. So this is so let's draw element H and K first. Okay, so I'm going to sketch element H and element K. Okay, so this is where my element H is, and this is my element K. Okay, so once you have done this, we can draw the position of the neutral axis where the elements are located. Okay, so where the neutral axis is, I'm going to sketch in green. So this is the position of the neutral axis. Okay, so this is known as our neutral axis. And this neutral axis is important, okay? Because if you don't know where the neutral axis is, right, you don't know how to calculate your moments, you don't know how to calculate your torque. Okay, so once you have done this, we are going to position the applied load. Okay, so you have 150 over here. Right, and then you have 200 coming towards us, which is a dot. If you look at the arrow, it's coming towards us, right? It's a dot. And then you have 50 pounds over here, and then 1, 2, and you have another 150. Right, you have 150 pounds over here. Okay, so that's how your loading condition look like now. Okay, so now we are going to find out how this element is loaded. Okay, so number 3 says what? Do not analyze the forces that are dots and cross. So anything that are dot and cross, when you draw them, don't analyze them. I repeat again, anything that is dot and crosses, don't analyze them. Okay, then you look at over here. The only force that you have to analyze based on this view is the what? Is the 150. Okay, is the 150. So the 150, right? What is the 150? The 150. Okay, so now everything we are going to analyze. Okay, we're going to analyze relative to elements H and K. Okay. So the 150 pounds, sorry, come on, Eugene. So the 150 pounds that you see over here, right? Do you see the 150 over here? It's going to induce a normal stress is equal to 150 pounds, and it's going to be what? In tension. Okay, you just put bracket positive, which is in what? Tension. Okay, so this over here is your axial load. And some of you might ask, Eugene, why is that? Why should it be 150 in tension? Yes or no? So if I were to make you recap what we taught in week number 2, okay? Remember we had a structure looks like this, right? We have a structure like this. Remember? Under eccentric loading, right? So we have, so if this is where our element is, right? This is where our point C. Point C is the point of interest, right? So if we have a load P over here, right? We automatically put a P over there. Yes or no? Right? And then it's going to induce a moment in this direction. It's also going to induce a moment in this. So this is our PZ PX. If I were to draw our transformation in this way. Right? So that is why, right? PX, okay, either on element H or K will induce a tension. Okay. Then the next thing is we look at moment in the Z direction. Okay. So moment is equal to force, or I'm going to write this. Okay, so we're going to find, okay, so we know this. We're going to find MZ. All right, we're going to find MZ. So I'll write this. So we know that moment is equal to force multiplied by perpendicular distance. Okay, right? So we know that the perpendicular distance, if I'm going to draw the arrow over here, this is our perpendicular distance. And as you can see, the perpendicular distance, right, is towards the what? Neutral axis, right? You can see that, right? The perpendicular distance is up to the what? Neutral axis. That's why identifying the neutral axis is important. So perpendicular distance, yeah, I'll write down here. So perpendicular distance. Okay, so perpendicular distance is distance between the applied force to the neutral axis. Okay, so for this case, we know that mz, right? We know that mz is equal to what? So it's equal to force, which is 150 pounds, multiplied by perpendicular distance of 10 inches. So this is equal to 1500